Alright, welcome. In this video, we're going to be talking about fitting functions to numerical data. And in this class, we're going to stick to linear, quadratic, and exponential modeling. So I think first what I want to do is just kind of remind you of the basic facts, what we know about linear, quadratic, and exponential functions. So a linear function, we know the equation for a linear function. Y equals mx plus b. That's an algebraic description of a linear function. Okay, graphically, we also know what this looks like. It's called a linear function because its graph is a line. Okay, numerically speaking, that's what I'm going to remind you about today that you learned about in Algebra 1, was that if you're looking at a table of values and the x's are evenly spaced, like 1, 4, 7, and 10, those are all spaced out by 3, we'd see a constant difference in the y's. That each time we were just like kind of adding or subtracting the same number. So maybe if I had 20, 15, 10, and 5, we'd see that each time we decreased by 5. Each time x got bumped up by 3, y decreased by 5. So that might be important for us. We're seeing that same number that we're subtracting or adding each time. Okay, and verbally, how would I describe this? I might say that a linear function has a constant rate of change. And by rate of change, I don't exactly mean those negative 5s, but I do mean, those numbers that we're seeing. Those are in some way depicting the rate at which y is changing with respect to x. Okay, we studied quadratic functions quite a bit in this class, so we know that, the equation for a quadratic, it's a degree 2 polynomial. Like ax squared plus bx plus c. Graphically, we know that that makes a parabola. And it can face upwards or it can face downward. Okay, numerically speaking, let me get you a table that's going to represent a quadratic function. Okay, so what we see when we investigate the patterns on the y's for the evenly spaced x's is if we go to do the same first difference thing, we see it's not constant. So I increased by 1, I decreased by 2, I decreased by, wait a second, that's not right. That's a little more like it. We decreased by 5, and then to go from -3 to -11, we decreased by 8. But then if we look a little bit more closely at what's happening with second order differences, they're constant. Okay, so what we would say is that the rates of change form a linear pattern. But this verbal description of a linear, quadratic, or exponential function, that's not really what we're concerned with in Algebra 2. That's something we'll talk about a whole lot more in AP Pre-Cal next year. So rates of change form a linear pattern. Okay, so again, like the rates of change being the things in blue, the first order differences, the linear pattern we're seeing, with that constant difference there in red. Okay, so that's how we'll see that we've got a quadratic function. Then an exponential function, okay, I might start with a graph, because we studied those recently, and we saw that they can be exponential growth, we can have also exponential decay, and we can move those things around, we can do transforms on them, but I think these are the two most basic types of exponential function. Algebraically speaking, that's y is some number times some base to the x. Okay. Numerically, that's what we're going to see for evenly spaced x's. Again, all of this stuff, we need evenly spaced x's. We'll see a constant ratio between the y's. So for this table, where the x's are spaced out by 2 each time, I'm going to see each time I go to the next y, I've multiplied by 5. Okay, and if we see this constant ratio, we're going to see exponential growth or exponential decay. And while there is definitely things that we could say about, the rates of change of exponential functions, we'd really be getting into the calculus of Algebra 2, and this is an Algebra 2 class, not a calculus class, so I'm just going to say this is where we're seeing constant growth or constant decay as we move from left to right. So let's do a couple of examples of this. So determine whether the data represents a linear, a quadratic, or an exponential function. So I'm looking at this, and maybe I'm just hoping that these will all come back linear. And so I'm expecting linear because that's what I want it to be. I see I've increased by 8 and then increased by 42. No, pardon me, increased by 40. Which would be a second difference of plus 32, but I don't see this as likely. And then I'm realizing that I went from 2 to 10 and 10 to 50 and 50 to 250. It's like the exact same values I just wrote in the example for exponential. So this is only going to be exponential because as I go from 2 to 10, I've multiplied by 5. 10 to 50, multiplied by 5. 50 to 250, multiplied by 5. Same thing over here. Okay, each time I'm multiplying by 5, so I conclude that it's an exponential function. Okay. The next one, I'm going to see, okay, I'm adding 2 to get from 12 to 14, adding 2 to get from 14 to 16. This is good, yeah, plus 2 every time. If I see a constant first difference, I'm going to conclude that this is a linear function. And then for the next one, I'm saying -4 to -1. Okay, it's like division by 4, but -1 to 0 is not division. So I'm going to say, okay, -4 to -1, I added 3. Then -1 to 0, I added 1. 0 to -1, I subtracted 1. That's a little weird. -1 to -4, I subtracted 3. Okay, so I need to look at the second order differences and hope that those are constant. If I go from 3 to 1, that's a decrease of 2. Yeah, 1 to -1, decrease of 2, another decrease of 2. I have a constant second difference. This thing is quadratic. And there's a whole lot of practice on this on the homework. So like if you're not feeling 100% confident, go do all 16 of those and check your work against mine on the solutions video because like there's a lot of practice. And so you'll be able to get this down. All right, now let's use some technology to fit equations to tables of data. So the first example is going to be exponential regression. And we are going to be looking at the value of an item which is decreasing after it was purchased new in 2008. And now we're going to be asked to, write an exponential equation that represents the value of the item t years after it was purchased. So I'm going to go in and change the kind of independent variable values in the table to be the number of years since 2008. So 2009 is 1 year after 2008, 2 years, 3, 4, and 5. And that'll keep our numbers much better in our equation. Okay, so we're going to need technology. So we're going to pull out a graphing calculator. I'll be real honest with you, I cannot figure out how to get the keypad to go below the display window on this program I'm using, so it's just going to look a little weird, but I'm going to show you how to use the calculator here. So we're interested in writing an exponential equation, so we need to get all of this data programmed into the calculator. So we're going to go program them into a list. So we're going to press stat, okay, and that's going to take us to the statistics menu. And then when it says edit, it means like, hey, edit these lists that we've got. So we're just going to press enter to edit the lists. And then in list 1, we're going to put all of our x values. And in list 2, we're going to put all of our y values. And so, time is going to be the independent variable. The value of the item is depending on how long it's been since 2008. So I'm going to plug in 0, 1, 2, 3, 4, and 5. Okay. Then I'm going to go over to list 2, and I'm going to plug in 40, 35 and a half, 2961, 21.2, 1573, and 1324. Okay, I don't think we should have to worry about this a whole lot when we're doing this type of thing, so we're not going to work with a whole lot of negative numbers, but I just want to point out that if we did have to put in a negative number here, we want to use this negative, not that, because it's subtract, and I don't really understand why there's a difference in the calculator, but again, I'm not a computer scientist, so I think that would be, I forgot some sort of difference there. Okay, I double checked to make sure I've typed these all in right. 1324, 1573, 2120, 2961, 35 and a half, and 40. Okay, feel good about that. So now it's time to get an equation. I go over here to the stat menu. Okay, back to where I started. Except now I want to calculate an exponential equation. So I flip over to calculate, and then I'm going to have to scroll down quite a ways, okay, to exponential regression, and then I'm going to press enter because that's what I want, an exponential regression. Okay, the x list is list 1 and the y list is list 2. Okay, I'm going to just always put my x values into list 1 and my y values into list 2, so I don't have to change that. And then since I'm working on this nice TI-84 color edition, we have the option to store the regression equation. I think I'm going to show you how to do that. So what it's going to do is it's going to generate an equation, and then if we needed to like use it, say to figure out when the value of the item went below $1, then we could just have it already in y equals. So I'm going to call for y1, and I can do that by accessing like the F4 menu. So I'm going to press F4, and then it brings up all these y's, and throw it in y1. And then we'll say calculate, like go. There we go. I was thinking about it for a second, and I've got myself an equation. So it's y equals a times b to the x. Okay, we're talking about value versus time, so I'm going to just say maybe value is equal to a times b to the t. So a is 43.223. And anyway, and just in general in this class, we're just going to round to 3 decimals. 0.789 to the t. And if you want to report more decimals, you're welcome to. We'll also point out that, when you store the equation into y1, that it is going to carry all of these decimals. So you might be off like in the last decimal place or something against, if you've got a friend that just was working with a TI-83 and just typed into 3 decimals into y1, you might have a slightly different answer, but it shouldn't be too far off. Okay, so notice when I press y equals, it's got it all loaded in already, and so I can, let me see if the stat plot's on. Okay, it's not on, and I actually, overall I wouldn't recommend that you turn it on, but I am going to turn it on so that we can look at what we're doing here. So we're going to zoom to stat, so zoom 9, and then see how it got all of those data points in there for me. And then this is going to be the exponential curve that best fits. And if we're interested in when the value of the item goes below $1, we're going to be interested in finding where the value of the item is equal to 1. Okay? So what I'm going to do is I'm going to just let the calculator do the work for me. We could solve that equation, v equals 1 algebraically, but it'd be pretty bad, and we could only get like an exact value in terms of a log, so we'll just solve this one using technology. So I'm going to graph y equals 1. And then I'm going to graph again, and I'm going to realize, oh man, the window's off. I'm just like too far down. I'm looking for something that's farther down than I can see. So I'm going to need to adjust the window so that the y minimum is, I don't know, maybe 0, so that we can see 0 to 44. Okay, and we can see y equals 1 specifically. So it's going to go through, it's going to plot that best fitting exponential curve, and then it's going to be over there, and it's like, I don't have enough x. Okay, I need to allow for more x's in my window. So then I'm going to go 5.5 didn't work, so maybe 50 will work. Okay, that'll be more than enough. And I'm going to just change the y scale so that we don't have to, I don't know if that actually makes a difference in how fast the thing graphs, but right now we're talking. Okay, it's plotting blue. Now it's plotting red. We see there's been an intersection, and we're going to calculate the intersection. So we're going to go to calculate, because that's the menu where all the good stuff is. We want an intersection, so we're going to choose 5. Okay, the first curve is y1, it's the blue curve. I'm going to press enter. Second curve is y2, it's the red line. Okay. Give it a guess. It doesn't really matter because there's only one intersection. We'll see a situation where it does matter later. You can go over, make it pretty close, and we see that that's x equals 15.874. And notice that for all t greater than 15.874, I wrote that down wrong, 874, okay, we're seeing that the blue curve is going beneath the red line, which means the value is under 1. Value is less than $1. That's how we're going to do that. Right, now let's do a quadratic regression. And this one is fuel economy versus speed, which is evidently somewhat quadratic. So we're going to start by writing a quadratic equation to represent the fuel economy of the car when it's traveling x miles per hour. Alright, so we're going to have to input the data into the list, so I'm going to go back to the stat menu. I'm going to edit the list, just like we did for the last one. Now I'm going to need to clear out this data, and so what I want to do is go like highlight L2, press clear, and then press down. Okay. Important that we do that because I know it's possible to like delete list 1, and I have not taught stat in a number of years, so I don't remember what to tell someone to do when they delete list 1 to get it back. If you do that, then I'll just send you on down to our stat teacher, and either one of them will be able to show you what to do. We're going to just type in the data. Let me do that for you. Figured you didn't need to watch me type all that stuff in. So I've got all of these. I'm going to double check my numbers. Think I did it right. 25.4, 27.3, 28.2, 30.1, 26.1, 25.7, 24.2, and 21.4 for 17, 20, 27, 33, 45, 58, 67, 70. All right, feel good about it. Because if you type in even one of these numbers wrong, you're going to get the wrong equation, and there's not much you can do for it after that. So it's really worth the double check there. I'm going to go in, and I'm going to go back to the stat menu. We're going to calculate a quadratic regression. That's option 5. Okay, X list, Y list, that has not changed. We're going to store the regression equation into Y1. We're going to get Y1 out of the F4 menu. And we'll ask it to calculate. And so it's thinking, and I get this. So I can write out my quadratic formula here. I might use Y for fuel economy and X for miles per hour. It already said X miles per hour, so I'm going to say Y equals AX squared plus BX plus C. So negative 0.007 X squared plus 0.710 X, and then plus 11.8996, that would be 11.900. Okay. And that's my equation. What is the fuel economy of the car at 40 miles per hour? So miles per hour, that's an X value, so I'm going to say X equals 40. They want to know what the value of Y is. Okay, but I'm going to show you a couple of ways to compute this on the calculator that's not going to involve you typing in the same equation that we've already done the once. Well, I'm going to say, okay, one thing we can do is we can graph this thing. I think I'm going to zoom. No, I'm going to need to really manipulate the window. So maybe I'll start with the standard zoom, and you'll see that it's kind of not showing us what we need to see. Oh, God, see, it's also graphing Y equals 1. Whatever. So I'm going to go into the window, and I'm going to say, well, back over here, I'm seeing speeds that are ranging from 17 to 70. So let's just do 0 to 100. So I'm going to do from 0 to 100. I'm going to just have it put the tick marks every 10. That would be fine. And then in Y, I don't need to worry about negative miles per gallon. I'm seeing stuff in the 20s and 30s. So maybe I'll say 0 to 50. And there we're seeing the stat plot, okay, which we don't really need to do any of the stuff we're doing. We're still graphing Y equals 1. That's still not going to be necessary. I'm going to clear that out. We're going to need to graph 25 later, but for now, that'll be good. Okay, what we can do if we want to figure out what's the value of Y where X equals 40, we can have it calculate a value. So we can go over here from the graph, calculate, again, where all the good stuff is, calculate a value, just option 1. And then we're going to plug in X equals 40, and it's going to give us Y equals 28.628. Okay. Another option that we have is we can go into the table. I don't do that very often in this class. But if you look at the table, default is it starts at 0 and bumps up by 1 each time. So yes, you could scroll down to X equals 40, but there's a better way. You can go into the table settings right here, and instead of having it just be automatically starting at 0 and bumping up by 1 each time, you can have it just ask you for the independent variable. I really like this. Now, I don't really understand how, I feel like I understand how this is supposed to work, but it doesn't seem to ever work for me, so I don't know about that. We're going to go to the table, and we'll see all of a sudden, okay, it's empty. We can type in whatever X we like, and we'll get 28.628, just like we got the other time. That's a couple of different ways we could figure out the value of Y, where X is 40, that doesn't involve us typing in, negative 0.007X squared plus 0.710X plus 11.9. Okay. Now, if we use the rounded off equation, I remember from class we got 29.1, so it is a little bit different. And I guess I'll just be super explicit with you on the quizzes and the tests, what to round to, but I don't know that we'll need to be using it all that often. So we're going to quit, and we're going to say, at what speed does this car travel most efficiently? Most efficiently, that sounds like a maximum. What would be the maximum efficiency? What's the maximum fuel economy? What's the maximum value of Y? So we're interested in finding the maximum value of Y. And that's going to happen. We're actually finding the x value that gives us the maximum value of y, and we found a maximum on the calculator in this class. Before we go to calculate, option 4 is maximum. Okay, that does look like it's to the left of the maximum, so I'll just use that. I'm going to keep scrolling to the right until I know that I'm to the right of the maximum. And then there's only going to be one maximum in there. So I let it look, and that's going to be where x is 48.686. And that's going to be, okay, the speed at which the car travels most efficiently. Notice that there's some sort of like a little bit of deficiency in our model though, because we know that at 45 miles an hour we got 30.1 miles per hour. But maybe this is a situation where like the car was going downhill, or there was a wind blowing behind the cars, something like that, where there was a little bit of error. That's why these points here on the graph aren't exactly on the parabola. That's why we're doing a regression. We're finding the best fitting parabola to these points. And then at what speeds does this car get above 25 miles per gallon? Okay, well, we're miles per gallon, that's a y value, so we're just going to graph y2 equals 25. Oops. And then we're going to press graph. And okay, we're seeing two intersections. So we're going to calculate the intersection between blue and red. And this one we're going to have to be a little more careful. We're going to give a guess, and we're going to make sure we're closer to the, the intersection that we want. And so the first one would be, so y equals 25. That happens when x is equal to 72.627. And also at, let's calculate the other intersection, calculate, intersect, first curve blue, second curve red. Guess I need to go over here quite a ways so that I'm closer to the other intersection. Now, again, I don't totally understand how the calculator works, but I do know that I need to, when we give it a guess, we need to get a reasonable guess. Otherwise, it's going to, just return this one to us, and we already know what that is. So x is 24.744. Okay. And notice that on the graph, between these two x values, the blue curve is above the red line. Okay, so then the blue curve represents the fuel economy, and that's above 25. So for x being between 24.744 and 72.627 miles per hour, the fuel economy will be above 25. And in this class, I kind of made the decision we're not going to do linear regression because, theoretically you're supposed to do it in Algebra 1. And if you're going on to statistics next year, you're going to do a lot of linear regression, and it's going to work exactly the same as this. So I'm just going to leave it at exponential and quadratic regressions, which are the two things we are requested to do in Texas Algebra 2. And, throw in those table problems where we identify what type of function that is, because that's just good algebra. But other than that, that's going to be all for this video. Thanks for watching.